Okay, thank you very much for the invitation. It's a pleasure to speak here. What I would like to talk about is some joint work with Malabika Pramanik. Malabika is over here, and if you don't understand something in my talk, then you should go ask Malabika because she can explain it better. Okay, so here's the question that we are going to consider. Basically, we would like to see whether there's some interesting and non-trivial analog of Semeradi's theorem in a continuous setting. Suppose that you have a set of real numbers. Actually, instead of real numbers, I'm going to use the interval from 0 to 1. It doesn't really make a difference and simplifies some technical things. Now, here's one possible naive analog of Semeradi's theorem for real numbers. Suppose that E has positive measure. Does it follow that E contains a non-trivial k-term arithmetic progression? Sorry, and A was supposed to be E. That's right. We want to know whether E contains a k-term progression x plus r, x plus k minus 1, r, with r different from 0. So here's a question that you can ask. Well, actually, it turns out that this is not a good analog of Semeradi's theorem for the basic reason that this is very easy. So what you do if you want to prove something like this is you use the Lebesgue density theorem. The Lebesgue theorem says that if you have a set of positive measure, then almost every point of that set is going to be a density point, which means that if I take almost any point x in the set E, then I can choose a small epsilon, a small interval around it, say from x minus epsilon to x plus epsilon, call it I, so that E intersected with I has measure at least something like 99% of I. I can actually take this as close to 1 as I like. And so if I take this number close enough to 1, I can find a copy of any finite configuration I want, for example, a k-term progression. Okay, so that was too easy to be fun. But here's a hard question. And this one is due to Erdos. Suppose that E is, again, a subset of the unit interval. I'm going to assume, again, that E has positive one-dimensional Lebesgue measure. I want to know whether E must contain a copy, or an affine copy of a given infinite sequence. For example, I could take the sequence 2 to the minus n for n ranging from 1 to infinity. Or more generally, I could take any infinite sequence an. Now, this remains open in this particular case. Basically, what we know at this time is that if we take an to be a slowly decaying sequence, if an over an minus 1 goes to 1, yes, we can assume without loss of generality that an goes to 0. If we assume that an over n minus 1 approaches 1 as n goes to infinity, so for example, you could take an equal to 1 over n, or anything decaying slower than that, then the answer is no. This is due to Falconer, and the proof is by explicit construction. You can construct a Cantor type set which avoids your sequence 1 over n, for instance. There are also other examples. Due to Kolontzakis and Bourgain. There is no example known of a sequence an, an infinite sequence, for which the answer would be positive. Okay, so that's the question that we really would like to solve, and if anybody here in the audience has any ideas, please let us know. Okay, so what do you do if you don't know how to solve a question? You look for something easier that you can solve, perhaps. So here's a question that we are going to look at. Let's look at finite configurations instead of infinite sequences. But instead of assuming that E has positive measure, I'm only going to assume that E has Hausdorff dimension close enough to 1. So here's a question. E is a subset of the interval from 0 to 1. I'm going to assume that the dimension of E is equal to alpha. And eventually I want to take alpha close to 1. Must E contain a k-term arithmetic progression? Actually, I'm just going to look at 3-term progressions, just to keep things nice and easy. X plus r, x plus 2r, with r different from 0. Turns out that the answer to this question is no. And that's due to Caletti back in 1998. In fact, he constructed something a little bit more difficult. That's a set of dimension exactly 1, which contains no additive quadruples. So in particular, that implies that the set contains no non-trivial arithmetic progressions. Now, it would be a little bit unfortunate if that was the end of the story, because we would have nothing to do for the rest of the hour. But now, what we can do is look at some things that people have been doing in number theory and see if we can maybe find some sort of inspiration over there. Specifically, if you think about that statement there for 3-term progressions as an analog of Ross theorem in sets of positive density, maybe it's an easy analog, but anyway, then something like this up here might be an analog of a Roth theorem in sets of density 0 in the integers. Now, it's known that in general, that sort of thing is not true. That's the well-known examples of Berendt and Salem-Spencer and other such. But it's also known that there are Roth-type theorems if you assume, for example, that your set, the one where you want to find an arithmetic progression, can be embedded in a random set with positive density. And that's the sort of thing that we are going to be looking for here. So let me state the positive result that we can actually prove. This is due to Malabika and myself. Here's a statement. Suppose that E is a subset of the unit interval. And we're going to make the following assumption. E sports a probability measure which satisfies the following conditions. First condition is that the, I'm going to call it mu here. The first condition is that the measure of an interval of length epsilon is bounded by a constant times epsilon to the power alpha for all positive epsilon, uniform in epsilon and x. And the second condition is that if we define the Fourier coefficients of a measure using the formula mu hat of k, where k is an integer, is equal to the integral from 0 to 1 e to the minus 2 pi I kx d mu of x, then we have a decay condition on these Fourier coefficients. Specifically, we would like to have mu hat of k bounded by some other constant c2 times k to the power minus beta over 2 for some beta greater than 2/3. Now, if we assume that alpha is close enough to 1, and how close is going to depend on the constants c1 and c2. It also depends on beta, but in most cases you can just take a beta fix. We don't really need the beta to be that close to 1. Anyway, so if we assume all of this here, then E contains a non-trivial 3-term arithmetic progression. I'm going to explain how this is proved in a few minutes, but first I would like to explain what these conditions here mean and why it makes sense to assume this sort of thing. The first condition is not terribly restrictive. Basically, we have, for any set E, the equality that the dimension of E is equal to the supremum of alpha, for which there exists a measure such that the first condition holds. This is the content of Frostman's lemma. It's one of the basic facts in geometric number theory. So basically, this is not the condition that you want to be worried about. Anytime you have a set of dimension alpha, you can choose a measure which obeys the first condition with maybe some slightly smaller alpha, but you can get as close to the dimension as you want. The condition that's much more restrictive is the second one, and I'd like to spend a few minutes on that. We're going to define something called the Fourier dimension of a measure. Sorry, the Fourier dimension of a set, excuse me. I'm going to use dimension sub f of E to denote it, and this is defined as the supremum of exponents beta between 0 and 1. Such that there exists a measure sported on E such that the second condition holds. For some constant C2. This definition is valid in dimension 1, if E is a subset of real numbers. If E was a subset of Rd, then this here would be D. It's a minor technicality here. Okay, so in general, it's known that the dimension, that the Fourier dimension of E is always less than or equal to the Hausdorff dimension of E. That can be proved using energy inequalities, for example. It's also one of the basic things in geometric measure theory. It's also known that the inequality can be sharp. For example, if you take the standard 2/3 Cantor set, so you start with the unit interval, you divide it in 3 parts, you delete the middle part, and then you iterate the procedure. Then that set has Hausdorff dimension log 2 over log 3, but it can be shown that the Fourier dimension of that set is 0. In fact, it's quite non-trivial to show that there are sets for which the equality can take place. And so somebody was saying something? I can't hear you.
You were saying instructor.
Sorry. I said the inequality can be sharp. So you can have this. That's the example. So it's actually non-trivial to see that this is not true. So there are actually sets for which you have equality. Such sets are called Salem sets, after the guy who constructed them first. The construction is a Cantor-type construction where you start with a unit interval, you divide it into some number of sub-intervals, then you divide some of them, and then you continue, except that you randomize the procedure, and then you prove that for a generic choice of parameters, you're going to get a Salem set. There are also examples due to Kahane. He starts with a pretty much arbitrary measure on an interval, and then he takes the image of that by Brownian motion, and that's almost surely sported on a Salem set. There's also a deterministic example due to Kaufman. There are also some variations on that. There's a construction by Bloom, which it's a modification of the construction of Salem. And there's also a new construction that we came up with that I'm going to mention in a second. Okay, so if we look again at the conditions in our theorem, it's similar to saying that E is a Salem set. You want to have a measure sported on it for which you have some pointwise decay of the Fourier coefficients. Now, it's not quite identical to saying that E is a Salem set. On the one hand, we don't require that beta should be equal to alpha or arbitrarily close to it. It just needs to be some number greater than 2/3, and then alpha can be something different. On the other hand, we have an additional condition here, which is the uniformity in constants. We want C1 and C2 to be fixed, and then we want to take alpha close enough to 1. So basically, it's not obvious that any set satisfying these conditions should exist. So we have to address that first. Fortunately, that turns out to come out just fine. So first of all, we checked whether these conditions, the uniform and constant version, is satisfied for the examples I mentioned here. Turns out that mostly it's fine. If you look at Salem's examples, turns out that the conditions basically hold except for a small modification in B, which is acceptable. Because our proof works under a slightly weaker assumption, which I did not state here for simplicity. Kaufman's example is explicit, so you can just look at the set and you can find explicitly a lot of arithmetic progressions in it of any length. If you take Kahan's examples, turns out that these conditions are not quite satisfied. Specifically, the first condition fails. It's only true with an additional logarithmic factor, which we don't know how to handle. But we can use a more direct argument to show that these sets also contain three-term progressions with probability bounded away from 0. And we also have a new construction given any alpha and beta, let's see, beta should be less than alpha, positive and less than 1, and any C1 greater than 1 and C2 greater than 0, we can find a set E and a measure mu on it for which these two conditions hold. Okay, I just noticed that I need to correct something here. This doesn't make a lot of sense when k is 0, so that's for non-zero k. Okay, so that's a couple of classes of sets to which our theorems can be applied. Okay, so let me now give you a short outline of the proof. So the general outline is a little bit similar to what you see in number theory, except there are various specific places where we had to do something a little bit different. So we start by defining a trilinear form. Mu is going to be the measure that we defined here in the statement of the theorem. And I'm going to define something called lambda of mu. This is going to be the sum over all integer k of mu hat of minus 2k, sorry, of mu hat of k squared times mu hat of minus 2k. That's an exact analog of what people work with in number theory, at least in the Fourier representation. The reason why we want to work with this is that it counts three-term progressions in the sport of mu. Now, this statement is actually a little bit non-trivial in this setting here. So let me write the first claim that I want to make. If the lambda expression is positive, then the set E contains non-trivial three-term arithmetic progressions. This is easy to see if mu is absolutely continuous. Let's say that it has density F. In that case, I can rewrite the lambda as a double integral of f of x, f of y, f of x plus y over 2, dx, dy. And I think there's a factor of 1/2 in front of it. That's basically a calculation that's identical to what people do in number theory. So you can see that if the lambda is positive, then that means that there must be some x and y such that f of x, f of y, and f of x plus y over 2 are all positive. So in particular, xy and x plus y over 2 are in the sport of mu. But actually, the absolutely continuous case is not the case that I'm interested in here. Because if mu is absolutely continuous, then it's sported on a set of positive measure, and I already explained at the beginning of my talk how to solve that case. So we are really interested in the case when mu is singular. And then there's a little bit more work to do. So what we end up doing is we define a measure mu on 0, 1 squared in 2 dimensions, such that mu is sported on the set X consisting of those pairs x, y, such that x, y, and x plus y over 2 are all in E. Mu of CO1 squared is equal to lambda of mu, mu, mu. So in particular, if the lambda is positive, then mu is non-trivial. And I also want the arithmetic progressions I get to be non-trivial, so I need to prove that mu of the diagonal is going to be 0. That's done by an approximation argument. It uses pretty extensively the second condition here on the measure mu. In fact, you need this sort of condition to even define the lambda thing in the first place, because otherwise the infinite series does not necessarily have to converge. The second step is, I want to prove the following. Let's look at the absolutely continuous case a little bit longer. Mu is going to be an absolutely continuous measure with density F. Okay, I have explained about arithmetic progressions in sets of positive measure, but actually we need something a little bit stronger. We need a quantitative estimate. Specifically, what we're going to need is that the lambda of mu, mu, mu is bounded from below by a constant. And that constant depends only on m, where m is a constant such that f, the density is bounded by m. Okay, so recall that I assumed earlier that mu is a probability measure. So if I fix that, and if I also fix a bound on the density of mu, then the lambda is going to be bounded from below by a constant uniformly in mu. Now, the qualitative statement to the effect that positive measure sets contain 3-term progressions was easy to prove. That was the Lebesgue density argument, but this turns out to be much more difficult because the Lebesgue density theorem does not give you any quantitative bounds. So instead of using something as simple as that, you basically need to follow the proof of Rouse theorem in number theory. Okay, the next step, and this is perhaps the most important, the most interesting one, is that we use something called a restriction estimate. This is something that I mentioned in my talks last week. Restriction estimates come from Euclidean harmonic analysis. The usual setup is where you have a curved hypersurface in d dimensions. But there are also restriction estimates in other settings. I have mentioned restriction for sets of integers. What we're going to be using here is restriction estimates for Salem sets. The first such estimate was proved by Mockenhaupt in 2000. And then we proved a somewhat different version of a Mockenhaupt estimate. Specifically, the estimate that we need is the following. If mu is a probability measure obeying the conditions A and B, then we have the estimate, the integral of f d mu, f squared d mu, where f is a function with values in, say, complex numbers. Square root is bounded by a constant times the LP norm of the Fourier series of f in Z. Now, this was first proved by Mockenhaupt for a certain range of p. We proved it for a range of p that's actually slightly worse. So specifically, we need it for p equal to 2 times beta plus 4, 1 minus alpha over beta plus 8 times 1 minus alpha. That's the one part of this talk that I can never actually remember. That's why I have the notes with me. The difference between Mockenhaupt's result and ours is that we needed an estimate where the constant c depends only on the constant c1 and c2 in the assumptions here. Now, those of you who are familiar with the Thomas-Stein theorem might be interested to know that Mockenhaupt's proof basically follows the proof of the non-endpoint case of Thomas-Stein, the Thomas argument. We had to follow Stein's endpoint argument instead. Okay, so now I can explain more or less the main argument. And this here follows, at least in the general outline, the arguments of green, and then later green tau, and tau v for sets of integers. Basically, we're using a continuous variant of their transference principle. We want to decompose mu as mu1 plus mu2, where mu1 is an absolutely continuous measure with bounded density. And that constant there, the m, is supposed to be independent of the C1 and C2. I'm sorry, I screwed that up. It is going to depend on C1 and C2, but it's not going to depend on alpha. The mu2 is going to be the singular part. It's going to be a little bit unpleasant, but at least it's going to have small Fourier coefficients. The way we come up with this decomposition is it's supposed to construct mu1, and then mu2 is just going to be whatever is left. And the mu1 is going to be the convolution of mu with the Fayet kernel. I'm just going to write out what that means in a second. K2n is 1 over 2n plus 1 times the square of the Dirichlet kernel, and that's the sum from k equal to minus n to n of e to the 2 pi I kx. Okay, and that gets squared. So this basically acts as a cutoff in the Fourier space. What we want to prove is that, first of all, mu1 has bounded density. And that follows from the restriction estimate I just wrote out here. And then it pretty much follows from the definition that mu2 has small Fourier coefficients. And then once you have that, it's easy to finish the argument. You write out the lambda expression again. And then you plug in the decomposition we just found for mu, so you get lambda of mu1, 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 which is going to be the leading term. And you have some number of terms with at least one copy of mu2. The first term, the one with mu1 terms only, is bounded from below. By the second step, by the Roth theorem. And here you just use that mu 2 has small Fourier coefficients. And then if you take the alpha close enough to 1, then this quantity here is going to be less than that, so you get that the lambda expression is positive, and therefore you get 3-term arithmetic progressions. Okay, so to finish, let me say a couple of things about what we don't know how to do. There's the obvious question of what happens when you take a longer progression, say 4 terms or k terms. We don't know yet. We don't know whether a Fourier analytic condition like this one here would be enough to guarantee that you have 4-term progressions in a set. It's known in number theory that linear uniformity is not quite enough to get the expected number of 4-term progressions. How that translates to this setting here and what the analog of quadratic uniformity would be, we don't know yet. Something else that we don't know is whether we can somehow get rid of this dependence on C1 and C2 in the conditions. Like, for example, suppose that we know that E is a Salem set of dimension 1 for some choice of constants. We don't know whether that set must necessarily contain a 3-term arithmetic progression. At least it does not follow from the argument that we have here. So that's something else that we don't know. And one more question that I'd like to mention is about the higher dimensional case. There's a variant of Samaridy's theorem in higher dimensions where you look for affine copies of say, configurations in a plane. Can you do something similar in a continuous setting? Now, in general, it's probably impossible at this point because, first of all, you would need to have a Fourier analytic proof of the multidimensional Samaridy theorem, and we don't have that now. But there is such a proof in one specific case where you just look at triangles in 2 dimensions with these 2 side lengths equal. So there's a Fourier analytic proof in this case. That's another question that perhaps it would be possible to address with the methods that are available. Suppose that you have a Salem set in 2 dimensions, or maybe some sort of a modification of these 2 conditions here. Is it possible to prove that such a set must contain a right triangle like this one? Okay, so maybe I should stop here. Thank you for your attention.